Quantum computing. Yeah, I know what you're probably thinking. Incredibly complex physics, impossible math, right? And sure, it can get pretty deep. But what if I told you that taking that very first step, writing your first Hello World program, is way, way easier than you think? And hey, you're not alone in feeling that way. This right here is a real post from someone on Reddit who is looking for a simple, visual way in. And honestly, that's the perfect request. So that's exactly what we're going to do in this explainer. We're going to build your first quantum program, visually, step by step. All right, before we write a single line of code, we just need to get our heads around two, and only two, fundamental ideas. These are the concepts that give quantum computers their insane power. Let's break them down. First up, the qubit. You know how a regular computer bit is just on or off, a 1 or a 0? Simple. Well, a qubit is where the fun begins. It can be a 0, it can be a 1, or, and this is the wild part, it can be both at the exact same time. This is called superposition. The best way to think about it is like a spinning coin. While it's up in the air, is it heads or tails? It's kind of both, right? Only when you slap it down on your hand, when you measure it, does it have to pick a side. And this is the perfect way to picture what that means. It's called a Bloch sphere. Now think of that normal bit as having only two options, the North Pole for a 1 and the South Pole for a 0. A qubit, on the other hand, can be any point on the entire surface of this globe. That's how many more possibilities, how much more information can be packed into just one of these things. The second big idea is entanglement. Einstein famously called this spooky action at a distance. Imagine you have two of those spinning coins, but they're connected, they're entangled. The moment one coin lands on heads, you instantly know the other one landed on tails, even if it's on the other side of the universe. Their fates are completely, mysteriously linked. Okay, enough theory, right? Let's make this real. We're going to take those two ideas, superposition and entanglement, and actually use them to build our very first quantum circuit using a tool from IBM called Qiskit. And you'll see the process is surprisingly straightforward. It's a pretty clear 4-step workflow. First, we map our problem into a circuit. Then, it gets optimized for the hardware. Step 3, we execute it. And finally, we analyze what we got back. Let's walk through it together. So, step 1, map the problem. What is our problem for this Hello World program? Well, our goal is to create something called a Bell state. Don't let the name scare you, that's just a fancy physics term for what we were just talking about. Two qubits that are perfectly, spookily entangled with each other. And get this, look how accessible this is. That code on the left, that's just 3 lines of Python, a language millions of people already know. And that's all it takes to generate the quantum circuit you see on the right. We're literally drawing a little map for the qubits to follow. So what did our code actually tell the qubits to do? It's really a simple 2-step recipe. The first command, that H gate, is basically like yelling, "Start spinning," to the first qubit. It puts it into that superposition state. Then the second command, that CX gate, is the real magic. This creates the entanglement. It's a conditional rule that says, hey, second qubit, look at the first one. If it lands on 1, you flip your state. And that one simple rule is what links their fates together forever. Now for the really, really cool part. We're not just running this on some simulator on our laptop. We are sending this simple circuit over the cloud to be run on actual physical quantum hardware at an IBM lab. For real. And this is where the Qiskit software is our best friend. Steps 2 and 3, optimizing and executing, are pretty much handled for us. The software takes our ideal little circuit, translates it into instructions the real hardware can understand, and then sends the job off to whichever quantum computer is free. It's awesome. So the job is sent, it runs, and a few moments later, we get the results back. The big question is, what did the quantum computer tell us? Did we actually create that spooky connection? And this is what we get back. Now, it just looks like a bar chart, but this is a snapshot from the quantum world, and it tells us everything. This chart shows the results of our experiment. So let's decode this. This is the aha moment. The first 2 measurements are asking about each qubit on its own, and the answer the computer gives us is basically 0. It's like it's saying they have no well-defined state by themselves. But then look at the other 2 measurements. These are checking for correlation, how the 2 qubits behave together. And what's the result? 1, a perfect correlation. And that, right there, is entanglement in action. The qubits don't have an independent identity, but their relationship to each other is perfectly defined. Their fates are linked. This chart is the data that proves it. We created that spooky connection, and this is the proof.
Okay, so creating a Bell state with 2 qubits is the hello world of quantum. It's the first step. But let's be honest, the reason everyone is so excited about this technology is what happens when you start to scale it up.
We just worked with 2 qubits. To solve problems that are actually meaningful, what's called utility scale, we need to be working with systems that have over 100 qubits. And here's the thing, the power doesn't just add up, it grows exponentially with every single qubit you add. And this isn't science fiction. The same documentation from IBM shows them running a scaled-up version of our experiment, creating a massive entangled state across 100 qubits. This is happening right now. But scaling up is not easy. This graph shows the biggest challenge. As you try to connect more and more qubits, this thing called noise, tiny vibrations, temperature changes, creeps in and corrupts the fragile quantum signal. Building machines that can overcome this noise is probably the single biggest engineering challenge in the field today. So why bother? Why fight the noise? Because quantum computers promise to solve problems that are simply impossible for even the biggest supercomputers on the planet. We're talking about designing new life-saving drugs, optimizing incredibly complex financial systems, or creating breakthroughs in artificial intelligence. And the best part is, you now understand the fundamental process. It doesn't matter if it's 2 qubits or 200. The workflow is the same. You map a problem, you create a circuit, you run it on the hardware, and you analyze the data. You've just seen the entire quantum development cycle, from start to finish. You've taken the first step. You've seen the evidence of entanglement with your own eyes. So the only real question left is, now that you know how it works, what problem will you try to solve?